So let's take a look here at this question and see what we know. Moxie is flying in a circle of diameter 3.5 kilometers. First thing I'm going to notice is they gave me diameter, not radius. So I'm going to write down radius, and I know it's going to be 1750 meters. Now, initially, we have an angle, and then you see 2 minutes later, another angle. So I'll write down time to be 120 seconds. Now, if I look at this right here, what is this describing? Well, this is describing her position. So if we draw this out on a circle right here, we'll see that position number 1 is south 30 west, so it's going to look something like that. And then the second position is east 15 north, so something like that. Now, if we want to solve this question, we need to figure out what her velocity is. So we know that the first vector for velocity is always perpendicular to her position. So v1 is going to look something like this, and v2 is going to look something like this. Now we know that we're comparing the velocity and the position. It's always going to be a 90-degree angle. So from there, what we can do is we can figure out what this angle is specifically. So let's go ahead, dot this out here. And we know from the Z pattern, back from grade 9 math, that if this angle is 30 degrees, this angle also is 30 degrees. Now, since the velocity and position angle is perpendicular, so it's 90, this has to be 60 degrees. So we can just take a moment and write down that our v1 is some sort of velocity at meters per second, but we know the angle is going to be north 60 east. We can do this again over here, except this time what I'm going to do is I'm going to draw this angle right here. So we know that if this here is 15, this one is also 15. If we draw down here like this, we know that this angle here has to be 75 degrees. So if that's 75 degrees, then this little piece in here is going to have to be 15 degrees as well, which means my velocity 2 vector is going to be south 15 east. I just realized that should be north 60 west. So from here, what we're going to do is we need to figure out what these velocities actually are, because we don't know. But we know we're producing 2 full turns and then some. And what does and then some mean? Well, it means when you're traveling from here all the way over to here. So that's like most of a circle, but not a whole circle. So how much is that actually? Well, from where we started, we know from position 1, we traveled 60 degrees, which is this spot right here. And then I traveled this next spot here, which is 90 degrees. And then this spot in here, which is going to be 75 degrees. But we also know there was 2 full turns, so 360 and 360. So we're going to go ahead, we're going to add all those up, and that's going to equal 945 degrees. We want to know the distance traveled. So degrees isn't going to help us out. What we need to know is we need to know radians. And if we compare radians to degrees, we know it's going to be pi over 180. So radians in this case is 945 times pi divided by 180. And when we go ahead and put them into our calculators, we find that the answer here is 16.49 radians. Why is this important? We know that velocity is equal to our displacement over time. In this particular case, the displacement is going to be the arc length, so the distance traveled. The thing is, we don't know the arc length, but we know arc length is equal to the angle in radians times the radius. So if I take my 16.49 and plug it in and times it by 1750, we end up with a distance of 28,857. So we can use this information and plug it into here. We know Moxie traveled 28,857 in 120 seconds, which means that she was flying at 240 meters per second. So we now know what these values should be for V1 and V2. The drawing is really hard to see with these vectors. And what we're going to do is we're going to rearrange it. Why are we rearranging it? Because we know average acceleration is equal to delta v over t, which is going to be v2 minus v1. Now, anytime we have vectors and we're going to do subtraction, we need to put them tail to tail. So let's go ahead and do that right now. My velocity 1 vector, we're going to take from up here, and it's going to be something like this. So that's going to be 60. And velocity 2 vector, we're going to bring down from the top as well. So it's going to look something like this. Now remember, what our ultimate goal is to produce a triangle, an isosceles triangle. And that's going to be something that looks like this. Remember, if this is v1 and this is v2, our delta v is always v2 minus v1. So that's going to be our vector right there. And for that, what we're going to have to use is we're going to have to use cosine law. So 240 squared plus 240 squared minus 2 times 240 times 240. We don't know what the angle is in here. So let's go ahead and take a minute to think about this. If this here is 60 degrees, then we know we've got 30 plus, well, all this in here, which is 90, plus this little extra piece right here, which is 15. So when you go ahead and plug this in, we end up with an answer of 443 meters per second. A vector isn't done unless we have a direction on it. So we're going to take a minute and try to figure out this direction. So I'm just going to move this off the page. And I'm going to take this drawing and make it a little bit bigger. Because I think it's a little hard to see when it's that small. So we're going to go ahead and we're going to put this out here. So there's my V1. And we know this is 30 in here. And we're going to draw my V2. And we know this is 15. So from here, our delta V is going to be the pathway between V1 and V2. So something kind of like that. So there's my delta V. So we know this is going to be an isosceles triangle because V1 and V2 have the same value. We know this is going to be 135. So to figure out this angle in here, it's 180 minus 135, which will be 45. But remember, that's between these two angles right here is equal to 45. So we know each angle, therefore, has to be 22.5. Now, we need to figure out this pink line here, its length. So what we're going to do is we're going to go ahead and I'm going to draw sort of an up-down axis so I can figure this out. So I want to figure out what this angle is. So this angle right here. Now, how are we going to do that? Well, if this value here is 30, then we know this value here has to be 60 degrees. And according to the Z pattern, if we know this is 60, then here it also has to be 60 degrees. But I'm not asking for that full 60. I'm just asking for this piece here that's in the gray. So therefore, 60 minus 22.5 is going to equal 37.5 degrees. So back up here, our change in velocity is south, 37.5 degrees east. We've now got enough information to solve for our instantaneous acceleration and our average acceleration. Average acceleration is equal to delta V over t. So 443 divided by 120. And when I plug that in, I end up with an answer of 3.70 meters per second squared. The angle hasn't changed, so it'll still be south 37.5 degrees east. Question's also asking for our instantaneous acceleration. You can use any of the formulas that are listed, but I see I've calculated my velocity, and I know what the radius is, so I think this is the simplest in this case to use. So I'm going to plug in 240, and then the radius being 1750. And when I do this, I end up with an answer of 32.9 meters per second squared. The question is, what's the direction going to be? So let's go back up here to read the question again. If we go up here, we can see the question's asking for the initial acceleration. So that's going to be specifically right around here. So let's go ahead and zoom in here, figure out what's going on. We know the original position was down here in the southwest. Now, if the velocity is heading this way here, in like a northwest direction, then the acceleration has to be pulling inward. So it's going to be pulling like this. So take a look what we formed here. We know we have an angle of north 30 degrees towards the west. Or sorry, north 30 degrees towards the east. And I will highlight it right here just so we see, because we've got north and then 30 degrees towards the east. Therefore, this is going to be the direction of our initial instantaneous acceleration. It's north, 30, east.